Hello everyone, and welcome back to our series on quantum mechanics. In the previous video, we discussed the double-slit experiment and justified the existence of the wave function. In this video, we will see how to analyze the wave function to obtain information about various quantities of interest, such as position or momentum. The wave function is the most fundamental mathematical object in quantum mechanics, as it stores all of the information about the state of a given system. By mathematically manipulating the wave function, we can extract any information that is physically retrievable about the system. Let's discuss some important mathematical properties of wave functions. For one, wave functions exist in a mathematical space known as a Hilbert space. A Hilbert space is a complex inner product space that is also a complete metric space. Let's dissect what this means. Firstly, completeness is just a regularity condition stating that the limit points of any Cauchy sequence in a given metric space are also contained in the space. This is just a fancy way of saying that there are no points missing inside it or on the boundary of the Hilbert space. A metric space is simply a space equipped with a distance metric, which as we'll see later is simply the norm induced by the inner product. A complex vector space is simply a space of complex valued vectors with properties such as closure under addition and scalar multiplication, as well as several other axioms. An inner product space is a vector space equipped with an inner product operation which satisfies the three following properties. In the case of a vector in Cn, this inner product is usually the Euclidean inner product or lowercase L2 product. However, for continuous functions, like our wave function in the position basis, we instead use the capital L2 inner product, which we define as the following integral over a general region. This L2 space, also sometimes just called the Hilbert space, contains all functions whose integrals of their absolute value squared are finite over a given interval from a to b. Note that if we have an inner product, we can define its induced norm as follows. This is the metric that I had mentioned previously. Norms have some useful properties, which I have listed here, such as absolute homogeneity and the triangle inequality, which are always useful to keep handy. Under this definition of the norm, we require that wave functions have unit norm. Note that since the norm is always greater than or equal to 0, we can write this statement in terms of the square of the norm without loss of generality. For instance, in the position basis, we impose the condition that the integral of the absolute value squared of the wave function across its entire support is 1. If you recall from the previous video, we established the Born rule, which effectively stated that the probability of finding a particle in an interval from x to x plus dx is simply the absolute value of psi of x squared times dx. Hence, this normalization condition is the same as the typical normalization condition for any continuous probability distribution. This means, for instance, that the probability that the particle is located somewhere between x equals a and x equals b is simply given as the following integral. In other words, all the normalization condition is stating is that the probability that the particle is located somewhere in the universe is 1, which should be obvious. As an example exercise, consider the following Gaussian wave function. What does the normalization condition capital A have to be for the wave function to be properly normalized? You can use an integration table for the Gaussian integral if necessary. Pause the video and compute the answer. Evaluating the integral, we get the following. Setting this equal to 1 and rearranging the coefficients, we have that capital A is given as follows. You should note that there are some instances in which we don't work with normalizable wave functions, such as when we are dealing with a plane wave in free space, and we will discuss how to handle and interpret these so-called free states accordingly when we encounter them. Let's now talk about some more properties of physical wave functions. For normalizable wave functions that are physically realizable, we usually also impose a few more regularity constraints that technically may not hold in general mathematically, but whose exceptions are too pathological to be relevant. For starters, for the norm to be finite, we must have that the wave function vanishes as x goes to plus or minus infinity. Furthermore, we also impose the condition that psi is continuous. Moreover, if we are dealing with the wave function in the context of a given potential, we assert that the first derivative is discontinuous only at the points where the potential is infinite and is otherwise continuous everywhere else. Okay. Now that we've established the basic mathematical properties of wave functions, how do we actually get the things we want from the wave function, like its position or its momentum? Well, in classical mechanics, we describe these quantities in terms of scalars and vectors. However, in quantum mechanics, these familiar quantities no longer correspond to numerical quantities, but rather operators. For instance, For a one-dimensional system, we have that the position operator is simply given by x. In other words, if we act with the position operator on a function of x, we have that the result is simply x times that function. I'm denoting that x operator on the left-hand side by putting a hat on it. I use this notation for clarity here, but keep in mind that these operators can also just be written without the hats. This definition of the operator may seem weird, since x psi of x doesn't inherently seem to tell us anything about the position. But bear with me, I'll explain how we can utilize the position operator to extract information about the position of a particle later in the video and in future videos. The other fundamental operator we often work with is the momentum operator. In the position basis, we write the momentum operator as negative I h bar times the derivative with respect to x. We can arrive at this definition for the momentum operator by considering a plane wave. As it turns out, a plane wave in free space, in other words where there's no external potential, has fixed energy, as you will see in a later video when we get to the Schrödinger equation. We can write the expression for this plane wave as follows. Here, I have substituted k for p over h bar and omega for e over h bar, where e is energy. Note that here we are discussing momentum and energy as numerical quantities. Taking the derivative of this function with respect to x, we get the following expression, which we can rearrange algebraically to get the following. This suggests the following general definition of the momentum operator. Note that in quantum mechanics, we cannot simply assume that observables commute with each other like we can in classical mechanics, where they're simply numbers. For instance, as we will soon see, the operators x and p do not commute with each other. We define the commutator of operators a and b as follows. Note that the commutator is 0 if and only if a and b commute with each other, as this means that ab equals ba. Let's compute the commutator of x and p. To do this, we can consider the action of these operators on a test function f of x. Expanding out the commutator, we get the following. Expanding this out using the product rule, we have that the commutator is given as I h bar, which is of course non-zero, indicating that these operators do not commute. Here are a few useful properties of the commutator to know for future reference. I won't prove these here, but they're fairly simple to show algebraically by just expanding the left-hand side using the definition of the commutator, and then just doing some generic algebraic manipulation. Okay, so we've defined these operators, but how do we actually measure these quantities? For example, if I have the wave function of a particle, how do I determine what its position is? Well, recall that in general, position and momentum are typically not localized for a generic wave function, and instead follow a probability distribution. Hence, if we measure the position of a particle, we are technically just sampling from this distribution at random. Okay, so the position and momentum of a system represented by the wave function is generally non-deterministic. But suppose we want to figure out what the average value measured is. For instance, what if we want to find the average position of the particle? This is also referred to as the expected value of the position, and we denote it as follows. Observe that this is identical to the definition of expected value in probability theory, as the absolute value of psi of x squared corresponds to the probability density of finding the particle at position x. Similarly, if we want to find the expected value of the momentum, we can write it as follows. Note that here, since momentum is defined as a differential operator rather than simply a function of x, we cannot rearrange this into the form we would normally use when taking the expected value of a classical probability distribution. In general, as you would expect, we denote the expected value of an operator q with respect to wave function psi as follows. It should be noted that once we measure a given observable like position or momentum, this changes the wave function accordingly in such a way that if we were to immediately keep measuring the state over and over without letting any time pass, we will get the same measurement outcome. We will discuss this in more detail in the next video when we formally define measurement in the context of eigenstates. With this in mind, you may be wondering how to interpret the expected value in this instance if measurement irrevocably destroys the original wave function. Well, you can interpret the expected value as representing the average measurement value of an observable we would get if we had prepared a bunch of systems in state psi, measure the given observable for each state individually, and then average the results. Drawing from classical probability theory, we can also define the variance and standard deviation of the position momentum as follows. Variance and standard deviation are measures of spread, indicating how concentrated the measurement outcomes are about the mean. A small variance or standard deviation means that these measurement outcomes are all very close to the expected value, while a larger value means that the measurement outcomes are fairly spread out from the mean. Note that a value of 0 means that we can exactly measure a given observable with exact precision. For position and momentum, we will see that it is impossible to measure both simultaneously to exact precision for a given state, as they are non-commuting operators. In particular, we have that the uncertainty for x and p satisfies the following inequality. This is known as the Heisenberg uncertainty principle. In the next video, we will see how the uncertainty principle generalizes to all pairs of operators. As a practice problem, try to find both the expected value and standard deviation of the position of a particle with the following wave function. Computing the expected values of x and x squared, we have the following. This gives us the following values for the mean and standard deviation of the position of the particle. Altogether, we provided a mathematical formalism for the wave function and explained how to extract information about a particle's position and momentum from its wave function. In the next video, we will continue our discussion by giving an in-depth rundown of the intuitive linear algebra structure behind quantum mechanics. I hope you enjoyed this video, and I will see you next time.